Hey guys, now I'm going to run through a couple examples of friction problems involving things on slopes or other complications. So here we are. This is a classic physics problem right here. We have a steel ramp with an angle of 25 degrees with a steel block on it, 8 kilogram steel block. That's what that says there. And what we want to figure out is, will the block slide down the slope under these conditions? So we look on page 138 and we see that the coefficient of friction for steel on steel is 0.8. So we will be using that. Okay, so this uses the skill that you've been doing with figuring out components of weight on a slope. What we're concerned with is the force of friction, which works up the hill, and the normal force, because we need that to feed our equation. The equation, as you know, is the force of friction, and this is going to be static friction in this case, is equal to mu static times the normal force. So basically we have to find numbers to feed particularly this one here, and then see if there's enough frictional force to overcome the downslope force. Okay, so the block has weight, F sub g, and that is equal to 8 times 9.8 meters per second squared. That's okay. People are working in here and just dropped a marble. That's fine. Okay, so the weight of the block is going to be 8 kilograms times 9.8. We're using our weight equation for that, W equals mg. And that comes out to be 8 times 9.8. Let's try that again. Nope. 8 times 9.8 equals 78.4 newtons. That's the weight coming straight down. Okay, now we're going to construct our triangle that we've been doing before. So this is the weight, 78.4 newtons. We have the normal force, which acts opposite the inslope component. And then we have the downslope force. So we're going to call this one F of x, and we're going to call this the normal force. Okay. Now, as you recall from last time, this angle up here is 25 degrees. That's the same as the angle of elevation here. And now we do our sine and cosine stuff. So 78.4 sine 25 degrees equals, and 78.4 cosine of 25 degrees equals. We'll figure those both out. Times 25 sine equals 33.1 newtons. And 25 cosine times 78.4 equals 71.0 newtons. Okay, now looking at the situation, we know that the normal force is the big one, so this equals 71 newtons. And the downslope force is equal to 33.1 newtons. Okay, that's the component of the weight which is acting down the slope. That is 33.1 newtons. Okay, great. Normal force we need to feed our friction equation. So force of friction is equal to mu times the normal force, which means that it is equal to 0.80 times 71 newtons. And that equals times 0.8. We use the same number that was there before. So the force of friction is up to 56.8 newtons, right? So that is the maximum force of friction that this system can produce. Remember, it's variable. The force of friction is less than or equal to this number here. But in this case, what we've just figured out is that the friction could be as high as 56.8 newtons. Now we compare that to the downslope force. The downslope component of the weight is 33.1 newtons. So that means that the gravity pulling it down the slope is less than the friction that can be produced. Okay, and that means that it will not slide. Okay, now I want to be very careful to distinguish here. The friction is not equal to 56.8. The friction is actually equal to 33.1 because the friction increases to match the pull that it's opposing. So there's 33.1 newtons of force pulling the block down. And what we figured out is there is enough friction to stop it from sliding. So the friction actually equals this number. But we have confirmed that there is enough friction to keep it from sliding down the slope. Okay? All right, next one. In this case, we have a wooden block sitting on snow, and we are pulling it like, say, a sled with wooden slats. And we are pulling upward on an angle to drag this thing through the snow. And we want to figure out how much force do we need to exert in that direction to keep the sled or the block sliding in that direction. Okay, so the complication here, it's twofold. First off, all of our pull is not opposing the friction. Some of it is trying to lift the block up. That's the first complication. That's the first complication. The second complication is that part of the pull is lifting the block up, which reduces the normal force of the block against the snow, which means that there's a smaller force of friction. So, big picture here, we have to split the pull into two components and then figure out what the vertical component does to the normal force, which will affect the friction, and then see what the horizontal force has to be to oppose that friction. So it's kind of a convoluted problem. It's not the simplest thing in the world, but we can do it. Okay, we're going to call this 35 degrees. We do need that angle in here. It's wood on snow, and when we look up on page 138, we see that the coefficient of friction, and this is sliding friction, so this is a mu s is equal to 0.06. And yes, you should look that up to see what we've got. Okay, it's a 12 kilogram wooden block on a snow surface. So let's try making some pictures here. So this is our force. We're going to call this Ft, the tension in the rope going up that direction. This is what we're trying to figure out is F sub t. This is a 35-degree angle, and we are going to figure out the horizontal and vertical components of the tension. Okay, now the vertical component, this one here, we're going to call this one Fty. That is equal to 30, it's going to be equal to the force of the tension times the sine of 35 degrees. Yep, and that will be the vertical component. Okay, so this vertical component is equal to whatever the tension in the rope is times the sine of 35 degrees. Okay. Meanwhile, the horizontal component, we'll need this later, Ftx is equal to Ft times the cosine of 35 degrees. Okay, we'll need that a little bit later. Now, our frictional force. Force of friction, and this is a sliding friction, so it's kinetic, is equal to UK times the normal force, which means we need to figure out the normal force. So the normal force is equal to the weight of the block, which is 12 times 9.8, 12 kilograms times 9.8 meters per second, minus Ft sine 35 degrees. Okay? What am I saying here? The normal force, that's the force of the snow pushing up on the block, is equal to the weight of the block, but the block is being lifted up a little bit. So this is the weight of the block, and this is how much it's being lifted up. Okay, Ft sine 35. All right, that's good. Now we need to know the horizontal force, which is required to, well, this will tell us the friction. Okay, so, oh yeah, I need to put this in here. So the force of friction, Ffx, is equal to 0.06, that's the coefficient of friction, times 12 times 9.8 minus Ft sine 35 degrees. And all of that is in parentheses because it's the coefficient of friction times all that, and all that is the normal force. Okay, so that's for our force of friction. Now, to keep the thing sliding, the horizontal component of the pole has to equal that friction. And we just figured out that the horizontal component of the pole is this term here, Ft cosine 35 degrees. So we're going to set these equal to each other. We're going to set the friction equal to the horizontal pole and see what we get. So this is the horizontal pole, Ft cosine 35 degrees has to be equal to 0.06 times the quantity. I'm going to just do 12.98 so I don't have to do it again. 12 times 9.8, 117.6. So 117.6 minus Ft sine 35 degrees. Okay, and now we solve for Ft. So Ft, the cosine of 35 degrees, is times 0.8192 is equal to 0.06 times 117.6, that is 7.056 minus Ft times 0.06 times sine of 35 degrees, because we're distributing the 0.06 across both these terms. Okay, so sine of 35 degrees is that. We're going to multiply that by 0.06 equals 0.0344. So this here is Ft times 0.0344. So now we're going to add this over on this side. So we get 0.8192 Ft plus 0.0344 Ft equals 7.056. So we're going to add this plus 0.8192 and we get 0.851 Ft equals 7.056. Divide that into 7.056 and we get Ft is equal to 8.3 newtons. Isn't that awesome? So we figured out that we have to have 8.3 newtons of force pulling up this way to keep 12 kilograms of wood sliding horizontally across snow. Alrighty, that's that.